Hi, I'm Eric, and let's talk about engineering. The unification of NPU drivers in the Linux kernel. The artificial intelligence ecosystem in embedded systems is currently in a state of technical entropy that threatens to stifle innovation before it reaches operational maturity. We are trying to build the future of neural processing on a fragmented software foundation, where each silicon vendor operates in its own logical fiefdom, creating a bottleneck that no large-scale deployment can ignore. This lack of cohesion is not just an inconvenience, it is a structural failure that prevents the technology from truly scaling at the edge. Historically, integrating NPUs has been an engineering nightmare. The prevailing model of proprietary drivers is not only inefficient, but also represents a critical risk to long-term stability and maintainability. In a forensic analysis of these systems, we observe that reliance on binary blobs and out-of-tree drivers forces developers to remain locked to specific software versions, making security updates or global performance improvements impossible. You cannot build a reliable system on a black box that does not communicate with the rest of the kernel in a standardized way. The technical movement toward creating an AI accelerator subsystem inside the Linux kernel, following the success of the direct rendering manager for GPUs, is the only viable path to maturity. The technical complexity is immense because, unlike CPUs, NPUs do not share common instruction sets. Each architecture manages memory and task scheduling in radically different ways. However, efforts such as the development of the IVPU driver for Intel accelerators and the standardization initiatives from Samsung and NVIDIA are demonstrating that unification is logically possible. From a systems design perspective, implementing a standardized user space API would change the rules of the game. It would allow high-level libraries such as OpenVINO, TensorFlow Lite, or ONNX runtime to interact with any compatible NPU without needing chip-specific patches. A fundamental technical advance here is memory management through DMA-BUF, which enables zero-copy data flow from devices such as cameras directly to the NPU. This eliminates unnecessary copies in main memory, reducing latency and power consumption, decisive factors in embedded hardware. As engineers, we must understand that standardization is also a security imperative. Open-source drivers integrated into the mainline kernel allow constant audits and a rapid response to vulnerabilities. The software lock-in imposed by proprietary drivers is a structural weakness that compromises the agility of any serious engineering project. Real competition among manufacturers must happen in silicon efficiency and compute performance, not in who has the most restrictive SDK. We are at a turning point. The current discussions in the Linux kernel mailing list about this new subsystem will define how we build AI systems in the next decade. The technical feasibility of a future with ubiquitous AI does not depend on creating more complex algorithms, but on consolidating this solid software foundation so that hardware can be truly functional, reliable, and transparent. The success of AI on Linux depends entirely on our ability to unify these drivers under a rigorous technical standard.